Hi, my name is Shantanu Gupta, and here I will be talking about the paper Eulerian Single-Photon mission. This is a joint work with Mohit Gupta from the University of Wisconsin and Madison. The background for this work is the standard noise versus motion blur trade-off in image acquisition, where if we have enough light, we can capture fine details with high FPS, but with a little noise. Low FPS removes the noise, but we lose details in the moving regions. This trade-off is directly passed on to downstream vision tasks, and here we see it for the case of edge detection. The problem becomes a lot worse in low light, as we can see here. Looking at the noisy case in more detail, we see that it suffers from two separate problems. The first is short noise from the random photon arrival process, and the second is readout noise from the sensor electronics. Read noise is a bigger problem at high frame rates or in low light because we have a weaker signal in those settings. One way to move past this issue is to use single photon sensors which don't have read noise. The resulting video has higher quality than the noisy one we saw before, but there are still problems. The photon noise is still there, and the single photon sensors have their own limitations in terms of having lower precision and also lower light efficiency than conventional CMOS sensors. So plugging these images into a standard vision algorithm can be difficult, as you can see from the edge detection result below. Another practical challenge is that a large volume of data is generated by these sensors. Here we see an example with a conventional CMOS resolution but a high frame rate, and we generate a lot of pixels per second. So we need an algorithm to be both robust and scalable. One way to do this is to one way to address these issues is to get better images. So a single frame by frame approach is shown here, which can work reasonably well, but there are still artifacts from the denoising because we have to impose a strong prior, and the time taken, the computational cost, is also non-trivial. We can improve the quality further by using a burst technique which takes motion into account, but it is even more costly. In our work, we propose directly processing the video as a 3D volume. So we convolve it with a bank of velocity tuned filters. These are complex 3D filters at multiple scales, and they are tuned to different combinations of spatial orientation and velocity. And the responses then encode motion and texture details at different locations, as you can see here. These responses are complex, and we use classic phase-based methods to extract scene details like edges from them. This can be done a lot faster than the denoising based approaches because we only process the video in a single shot. And also, we are still robust to noise because information is aggregated across space and time by the filters. The reliability of the filter responses can be estimated, and we provide more details on this in the paper. The motivation for using phase-based methods is seen from this simulated example where we have a simple sinusoid being imaged by a single photon sensor. In this case, it's a binary 1-bit sensor. If we look at the Fourier coefficient of these samples, we can see that the amplitude is not close to the original wave, but the phase is, and that can be read out so quickly because this is just a single Fourier transform. Our approach for video is similar but uses wavelengths. Here's a video taken with a real single photon sensor. In this case, there is very low light of about 2 photons a pixel. From this, we can get edges in both moving and static regions, and we can also get optical flow type estimates of motion. Since edges are estimated in 3D, we also have their 3D orientation, and that directly corresponds to a velocity, and we can see that here. Here we have a scene with high dynamic range and also some very faint edges, such as on the floor. Here's a scene with fast, non-rigid motion. In this case, we have motion estimates at 2 scales on the right, and in the middle we have separately calculated edge velocities. This is the same experiment but with a different scene with low light. That's it. Thank you for your attention.